Yeah, so I'm going to talk about some of the latest, what we've started working a couple of years back. What you see there is, wait, I have to switch to the other screen, I guess. No. Yeah, so I get asked a lot. So is this tweezer arrays of atoms or molecules? And what people typically do not ask is if it's tweezer arrays of nanoparticles, it's tweezer arrays of nanoparticles. Doesn't matter. I mean, whatever you actually, whatever behaves as an induced dipole, you can trap in a dipole trap, and you can image it very nicely. And all of the physics that I showed today, you can do with either of these three systems. We chose nanoparticles because they scatter a lot of light, so we can detect it easily on cameras and on homodyne and heterodyne detections. And they also don't move a lot because of their mass, but in principle, all of these studies could be also transferred to other fields. And because Marina asked me also to give a bit of a historical overview of the field, I have to go back not something like 10 or 15 years, but more like 55 years to 1970, when Arthur Ashkin published his first paper on acceleration and trapping of particles by radiation pressure. And in it, he writes, this letter reports the first observation of acceleration of freely suspended particles by the forces of radiation pressure. And later on, the point is the ideas can be extended to atoms and molecules, where one can predict that radiation pressure from tunable lasers will selectively accelerate, trap, or separate the atoms or molecules of gases. So in his paper, what he showed that in a glass cell filled with a liquid, you can have counterpropagating laser beams, and that would stop the motion of a small microparticle at a time. So we are talking about something like 20 microns in size, something that you can see with a regular microscope. And he very well explains how the trapping force actually come along due to the momentum transfer of the light as it refracts through the microparticle itself. And this is how it started. It was a toy project by him. So I mean, it couldn't have started if lasers weren't made just a few years back. So after that, of course, he went on to a whole endeavor of studies. But it also branched out into atomic physics. So in his Nobel Prize lecture, Bill Phillips says, in 1978, while I was a postdoc at MIT, I read a paper by Arthur Ashkin in which he described how one might slow down an atomic beam of sodium. And that paper was my first introduction to laser cooling, although the idea of laser cooling has been proposed 3 years earlier, independent papers by Hensch and Shellow and Weiland and Demelt. And although the treatment in Ashkin's paper was necessarily oversimplified, it provided one of the more important inspirations for what I tried to accomplish for about the next decade. So I think just a year after 1978, Bill Phillips moved to Maryland and started his experiments on laser cooling, and later on got the Nobel Prize. So now we are 1978, 8 years later, 1986. Steve Chu joined Arthur Ashkin and started pushing for trapping of atoms, and they realized the first optical dipole trap. This is a cloud of 500 sodium atoms, a picture from their paper. And they discuss how you can have a optical dipole potential that depends on the intensity of light, the line width of the atomic transition, and one over the tuning from the atomic transition. And now if you flip the sign of the tuning, positive or negative, you can have a repulsive or attractive potential. But although this was published in PRL, the same paper, there was a paper, same year there was a paper about trapping micro and nanoparticles, even down to 25 nanometer, which was published just in Optics Letters, right? People were jumping on this possibility because it was opening up a path, not yet to BECs, although I mean this was also used in creation of BECs, but later on to now what we have as optical tweezer arrays. And if you write the dipole potential for the levitated particle, you see that it's also the intensity, and you have this factor here that is called polarizability. And for dielectric materials, it's always a positive property, so you would always trap it in the intensity maximum. And you cannot switch the sign unless you have, for example, a plasmonic particle, if you want to use that in trapping. And you see, I mean, this polarizability, you can also actually consider that to be a classical polarizability model, the Lorentz model of induced dipole of an atom. So actually, these two equations are completely the same. You can make complete parallels between the two of them. And this is how it actually looks like in our lab. This is one of the silica nanoparticles, glass, that is around 150 nanometers in diameter. This is an SEM picture. Just for you to know, it has about 2.8 pentagrams or 10 to the 9 atomic mass units. There are no internal transitions in this body, so there are no vacancy centers, no doped ions or anything like that. We look only into their motion in optical traps. And how much they scatter? Well, 10 to the 14 photons per second. So you can blind your camera. The image that I showed you on the title slide has, I think, a neutral density filter of, I think, 4 orders of magnitude or something like that. And if you shine a laser beam on it, so if you trap one of these particles and you shine a laser beam from this side following the arrow, and it's polarized out of the screen toward you, and you look into the scattered light, you will see a ring. And this ring comes from the fact that this particle is smaller than the wavelength of light, so it's an induced dipole. And induced dipole radiate like dipole antennas. So there's no scattering of light along the polarization. So if you manage to turn the polarization of light, then you can rotate also your scattering pattern from having a donut to a ball, and so on as you follow the circle. And again, for some of you that have some experience maybe with atomic physics, polarizability of one of these particles is equal to the polarizability of a cesium atom 50 megahertz of resonance. So it's essentially a farly tuned atom. And this means that, of course, you can trap it in an intensity maximum. And the induced dipole radiates with the same frequency and in phase with the red-tuned driving light. So that means that the photons that are being scattered off the particle into free space have the very same frequency and preserve the phase of the incoming light itself. And light is scattered in a dipole radiation pattern. We've already seen that, and you can trap it. So trap depth is larger than 5,000 Kelvin, so you don't need to do any cooling of its motion. It stays there in room temperature. And you typically use around 100 milliwatt of optical laser power to trap with a mechanical frequency of 200 kilohertz. Okay, so just to give you a bit of an overview, you can write a Hamiltonian on the interaction that you can then, calculate the gradient of the intensity of the light field, and then you can get the potential energy. From that, you can calculate the mechanical frequency. And however, when the particle starts moving, then it also induces a little bit of inelastic scattering, right? So depending how it actually moves, you can give some momentum to light as well. So you can have momentum exchange, and that leads to stoked and anti-stoked sidebands. So basically sidebands that take and give one photon of energy to this to the motion of this nanoparticle. This is how when we measure with the detector, we get a record time trace like this, and it's completely random, of course, because it's in a vacuum chamber, but there's still a lot of gas around. So we're talking, this measurement was done around maybe 10 to the minus 1 millibar. We can go down, of course, but we wanted to show some stochastic behavior. So sometimes, it oscillates with a high amplitude and then it decays. This decay time is given by the damping of the gas. And on the other side, the periodicity, of course, is given by the mechanical frequency. So all of our measurements, what we do is we evaluate, we go into the Fourier domain to evaluate power spectral densities, because that gives you an ensemble average of all of the motion. And then you can really fit that with a function that is called a Bright-Wigner function, which is similar to a Lorentzian. Where you get the line width for the full width half maximum, and you get a peak of the mechanical frequency. And most interestingly, the energy of the motion is the variance of its motion is the area below this curve. So you can just take a long time record, and then you can average for some time to generate a power spectral density that is like this. And from that, you can get the properties of its motion. So to give you this, why this system is so unique compared to other optomechanical systems out there, it really gives you some unique possibilities for control. And our work a couple of years back, where we focused on doing ground state cooling of its motion, so trying to prepare this motion of the nanoparticle down to the level of 0. Of course, it's a thermal state, so it's going to be some probability in being the ground state, some probability being the first excited state. But as we define ground state, it's to have more than 50% of time in the ground state of its motion. And you can trap the particle, as I told you already, via this focused laser beam, the optical tweezer. And then you can put it in a cavity and you can drive the cavity from the side. And then if the particle moves left and right, it's going to change the cavity resonance frequency because it's the electric material that has a higher refractive index than the environment. And if it does that, then the intensity of the laser beam is acting back on the motion to try to stop it. And this is the original cavity cooling by dispersive shift, or how they call it, dispersive coupling. And something that is now unique really for induced dipoles like atoms, molecules, or nanoparticles is that you can also actually tune the cavity to be almost resonant with a tweezer beam, and then you are actually collecting the scattered light from the particle with the cavity itself. And this realizes the third type of interaction that is now called coherent coupling. The maximum of this interaction is the intensity minimum of the cavity, and that comes with a lot of benefits for cavity cooling. Essentially, we collect only Stokes and anti-Stokes photons. There's no elastic scattering that's suppressed. And you can parameterize everything with a Purcell factor, so it does not depend on the property of the object itself. It can be an atom, it can be a molecule, whatever. Whatever is a nano object or smaller than the wavelength of light, you can put it like there and just use the scattering to cool its motion, and you would cool to the very same temperature, to the very same occupation, which is funny because the size of the object does not matter at all. So this is how one of the levitated particle actually looks like. It's the same one that I showed you before with a donut radiation pattern. And this is the trapping microscope objective here on the bottom, and this is the lens that collects the light that is being transmitted in the forward direction. And some of the things that people have been going to do in the field, I chose to show like 4 different fields where this can go to. So for example, quantum gravity is something that people would really like to do. Of course, these nanoparticles, they have really small mass, so you cannot really detect gravity from them. But everything that people develop as quantum control techniques in the field can be used even for bigger particles in the future. And this is why a lot of people are doing that, including the new faculty here at UC Davis, Nancy Agarwal. And then you can use it for quantum sensing. So these particles can sense incredibly small forces. And because you use optical tweezers, you can push them close to any surface. So you can measure, people are trying to measure gravity at short scales, Casimir forces, black body radiation forces as well, because this particle is smaller than the thermal wavelength of light. So it's not unknown actually how it emits black body radiation. You can use it for quantum antibody physics, and this is going to be my talk. So this is in the direction where we are going to, and I'll show you how we can do some interesting experiments. And you can use it for quantum metrology. So what people are also trying to do, also us a little bit in the lab, trying to see how we can, for example, use quantum resources like squeezing or entanglement to detect better and detect fundamental forces. So there's also people that can levitate many of these particles, like the group of Dave Moore in Yale, trying to detect potential dark matter kicks. So if a dark matter is a particle, then as it goes, it can give a momentum kick to an array of levitated particles. So the field is quite broad, probably hundreds of groups around the world already doing some optical levitation of nanoparticles, and the field is still growing. So now to go into this part here, couple of years back, we went a little bit again to the history, to 1989, to a paper in PRL by Burns, Fournier, and Golovchenko from Harvard, where they say Ashkin and others have shown that gradients of time-averaged optical fields can produce forces on microscopic dielectric objects. Here we call attention to the apparently little-known fact that intense optical fields can induce significant forces between microscopic aggregates of dielectric matter. So what I did is essentially the same experiments as Arthur Ashkin. So you have counter-propagating laser beams. This is most of the studies in this optical binding community. You trap one particle, but then you also allow that more particles can be trapped. And as a second one is falling in, you have coherent scattering of light back and forth, and you create kind of a miniaturized standing wave between the two particles. So the light scattering events interfere with each other, and the depth of these small potentials is enough to actually localize the particles in one of them. So you really create a crystal of particles with a spacing of multiples of lambda half. And if one of the particle moves, then it wants to pull, of course, the standing wave itself, and that also exerts a force on the other particle as well. And this was done with microparticles, again in liquid, because this is how it was the easiest to be done. So couple of pictures. This is from the group of Monica Rich-Marte in Innsbruck. Again, this is all liquid, and then you have two fiber tips, and the laser lights, laser beams come out of them, counter-propagating trap, and then there's 4 traps here trapped in a crystal. And then this is a picture from our collaborators of Pavel Zemanek in Brno, where there is more than 10 particles, and you can configure, geometrically, you can have whatever you want of laser beams, and then you will create some geometric patterns. But these were quite unstable in vacuum. So all of these experiments were done in liquid, because if you would try to pump the air out of your vacuum chamber and do the same things, the particles would disappear. And again, big particles, so we're talking definitely more than a micron, but going up to 20 microns, 50 microns, all sorts of sizes. What we do is we break the symmetry of the system, and we use optical tweezer arrays, because that allows us to trap nanoparticles, so going down, system that we can push into the quantum regime, because we know how to do ground state cooling. And we can independently control then the distance between the particles. So we can probe beyond the crystalline arrangement of particles. We can probe, we can change individually the optical phases. And of course, that means also that the phase of the scatter light between the particles also changes itself. So you can change the interference between them. You can change also optical frequency. I'm not going to talk about that. That's something that we can discuss later if you're interested. You can independently also change optical powers. That changes the mechanical frequency. So you have fully tunable system to really probe these forces. And to give you just an example of an interesting phenomenon, if you have the same optical phases, really, so phi 1 and phi 2 here, which are not shown, are completely the same. The system is fully symmetric. You can cut the screen here in half, and you would have a mirror image. One trap and one particle would be the mirror image of the other one. But if you actually break this symmetry, and with the specific case where I choose minus pi half of the phase on the left and 0 phase on the right, and I choose the distance to be also such that the light traveling from one to the other one will be also pi half, then we can do this following exercise. So the light scattered from the right particle will come with a phase 0. So this is shown here as kind of like a maximum of the electric field. I choose this convention. And then as the light travels, it acquires a traveling phase, right? And when it crosses to the other particle, the electric field is actually 0 there. And in the other direction, you start with a delay of minus pi half. So it scatters left and right with this delay, right? And on the right side, it overlaps fully in phase with the scattered light from the second particle. But on the left side, there is going to be destructive interference. So you can actually create potentials where on one side, or for one particle, you have a maximum addition of the potential to the particle. And on the left one, you actually have destructive interference. So you change both potentials locally, right? So, and if you change it locally, if you cannot write the global change of the potential, in this case, you cannot, well, then the whole system dynamics cannot be Hermitian, right? So this is why it actually becomes interesting. So if you calculate the forces are maximally non-reciprocal, because it's not that F21 is minus F12, they are actually the same in magnitude and following each other. And in the non-reciprocal community, this is called predator-prey dynamics. And how we call it is anti-reciprocal interaction, because it's exactly opposite to the non-reciprocal interaction. How it looks, I also wrote it here. It's highly nonlinear function as well. So it's a nonlinear function because there is a trigonometric function sine of the distance between the particles. So if the one particle moves, it moves a lot, it's not going to be the linear response of the second particle. And this is also what is interesting. You'll see in a couple of next slides. So non-reciprocal interactions do exist in nature everywhere, right? So the spiking of neurons in your brain is non-reciprocal because it flows in one direction. Flocking of birds is non-reciprocal because they follow each other. So the bird can only see the bird in front of it, not behind. You driving the car, it's also highly non-reciprocal. Social interactions, I like this from one of the Nature Nano reviews, can also be highly non-reciprocal, right? So all systems in biology and social sciences are non-reciprocal. And then the question is, can you also find it in the quantum domain? So you can find it in technology. I mean, if you work in the lab, you have probably used a Faraday rotator, which is highly non-reciprocal device. Electronic diodes are also non-reciprocal devices. And then the question is, right, so can it exist in the quantum domain? So if you use a closed quantum system to describe your system, so if you can write Hamiltonian of your system, if you can write only unitary and Hermitian dynamics, well, then everything is reciprocal. But some systems do talk to the environment, and in that case, there is dissipation and drive, and then you turn to the open quantum system. And in that case, the dynamics is non-Hermitian. But non-Hermitian does not have to be non-reciprocal. So there is a general rule that if you have a non-reciprocal system, so non-reciprocal interactions, then the system is non-Hermitian. But if the system is non-Hermitian, does not have to be that there are non-reciprocal interactions in them. So one has to be a bit careful. So non-Hermitian dynamics always occurs in open quantum systems. And the question is, can we also engineer non-reciprocity? I had an example here. So if you talk about non-reciprocity, people typically venture into optical non-reciprocity, and this is created due to the magnetic field. So it's called the Lorentz reciprocity theorem, and it's guaranteed for systems except in cases of magnetic field. So you have, for example, magneto-optic effect or chiral atom scattering, so in vicinities of nanofibers or nanostructures. So Faraday isolator is one example. I will just skip through this because some of you probably already work with that. The other system that you can also get non-reciprocity is nonlinear system. So it's a product of three operators in the Hamiltonian. However, the non-reciprocity does not arise until you linearize the system. So you use the nonlinear interactions, the nonlinear Hamiltonian to produce linear non-reciprocal interactions between ingredients. And this typically requires large magnets, so miniaturization is hard. So people try to do synthetic magnetic fields. And this you can generate in a following way. So if you want to generate non-reciprocal interactions between bosonic modes 1 and 2, you generate first a coherent reciprocal interaction, but where you can also engineer a non-trivial phase, phi 1, 2, that is not zero, right? This is completely Hermitian, right? This Hamiltonian. So it's going to swap the excitations with a certain phase, and this phase is changes sign, of course, in opposite directions. And then you bring another third auxiliary mode or a common bath, and you produce again these coherent interactions with this third mode. But this third mode has to dissipate into the environment to be the strongest one. So for example, you can imagine having 1 and 2 bosonic modes in a cavity, and number 3 then is a cavity mode. Actually, you have, as you very well know, you can have Hamiltonian interactions with the cavity mode, and the cavity dissipates into the environment, so it loses photons. So if you follow a bit of math, so you need to have broken time reversal symmetry, where that means that the phase that you acquire in one direction, so let's say counter-propagating or counterclockwise, it's not going to be 2 pi. Then in that case, you can actually trace out the third mode. You can represent it with a bath, and this bath will dissipatively couple. So notice that there was this dissipation rate of 2 gammas here. This is going to be equally then split to coupling to mode 1 and 2. So that means a diabatic elimination of your cavity mode. And actually, you can rewrite that as non-reciprocal interactions, where lambda is the original strength of the mode of the reciprocal coupling between modes 1 and 2, and then you have the additional dissipative coupling between 1 and 2 through the bath, right? So bath is not does not have to add noise to the system, but there is correlated noise coming through, and this is how you can couple them non-reciprocally. I recommend reading these lecture notes by Ash Clerk. They're really amazing to understand this topic. And Some of the applications in the recent years in experiments have been in optomechanics, for example, for studying non-Hermitian and topological physics, so amplifying signals over classical noise. So an experiment from Verhagen group in Amsterdam, they add more modes, and they are able to do something called quadrature non-reciprocity. So they're able to sense this small perturbation epsilon that you see there, exponentially increase sensitivity as they increase the chain length over the classical noise. Of course, you also amplify quantum noise, but if it's the classical noise limiting you in your experiment, you can win. Okay. And another example in AMO, I mean, you do Floquet engineering for synthetic gauge fields. So, for example, in group of Monika Eidelsburger in Munich, they do high-frequency drives of their lattices of atoms to engineer, again, this non-trivial phase loops inside of their lattices. So these are all examples of these non-reciprocal systems and how you can engineer. And in our research, we do a little bit of everything. So we look into light-induced dipole-dipole forces. These are the optical binding forces that I've told you about before, but now because we bring them down to the level of induced dipoles of small nanoparticles, we can really look into the quantum origins of these interactions. We look into collective quantum effects in non-reciprocal systems, so novel concepts like non-reciprocal frustrations in analogy to geometrical frustration in Ising chains, or non-reciprocal and non-Hermitian phase transitions. And cavity engineering of quantum states is something that we still continue doing, so now extending to tweezer arrays of nanoparticles and how we can use these interactions and all the tunability that we have to, for example, entangle and generate protected, actually, entangled states such that they can actually be used later on for some sensing. And so together with our theory collaborator, Ben Stickler from Ulm University, we did a full quantum modeling of this. And as I said, you have to take into account, if you want to do a proper quantum modeling, you need to take into account also the whole environment. So you need to quantize all the light modes that you have in your system, not only the lasers, but you have to quantize the free modes that you have that are actually mediating the interaction between them, because you have a infinite number of them and they all contribute to the interaction. And if you then trace out all of the light modes, you come down to the simple equations of motion. So oscillator 1, acceleration Z1 and Z2 has this interaction matrix, which is non-Hermitian interaction matrix. And again, you can call it non-Hermitian matrix or non-Hermitian dynamical matrix or non-Hermitian dynamics. There is no non-Hermitian Hamiltonian. I mean, sometimes in some cases you can write an effective Hamiltonian, but there is no such thing as non-Hermitian Hamiltonian. And if you do this quantum modeling, you get these non-reciprocal interactions. So you have off-diagonal elements that are non-reciprocal in coupling rates, but you also get correlations of the noise through the bath. And how you can actually think about it is that, you know, you have a shot noise of laser, and a photon coming from the shot noise kicks one particle and it gives a momentum kick to it, and then it kicks the other particle as well, and it gives a momentum kick to it, and then you create momentum correlations between the two, and these are actually conveyed then in the correlated baths of photons in this particular case. In our first experiments, we use a spatial light modulator to trap two particles. This is an image of these two particles, and we explored almost fully reciprocal interaction. And now if you plot the power spectral density of the motion, you see two peaks, and these reflect the normal modes of the system because they interact. So you have a common mode where both particles move in phase, and a common mode where they move out of phase, and the splitting between the modes gives you the coupling rate. And you can scan that with as a function of optical power, so you can really see an avoided crossing between the two different modes. And here the coupling rate was positive, but now the coupling rate depends as a cosine function of the optical phase difference. So if you flip that from 0 to pi, you can also have negative coupling rates. So you have anti-restoring spring between the two of them, if you can imagine how that would actually look like. Where the meaning of the modes actually flips. And you can do that as a function of distance, where you see that it oscillates with a period of lambda, telling you that it's really the constructive interference of light that leads to these interactions. It falls down as 1 over the distance, and this is because it's all in far field. The distances between them are much larger than the wavelength. And you can also turn the polarization. If you remember that there is no scattering of light along the polarization. If you turn the polarization, then you actually can completely suppress the light-induced dipole-dipole coupling, but you can then charge the particles to 100 charges each. This is also what we can easily do in our experiments. And then you see purely Coulomb coupling between the two of them. And now we have a separate experiment where we are trying to entangle the motions via Coulomb coupling, so kind of a tabletop experiment that will tell us a lot. What do we need to do if we want to repeat that with gravity and larger masses? The spatial light modulator was just available at the time. At the same time, we started building a full setup for such experiments where we use acoustic optical deflectors, because there you can also change the optical frequencies. So you can tune, you can create small arrays like 2 by 2. And because you drive them with the same radio frequency tones, you have diagonal laser beams that have exactly the same optical frequency. And you can then select these with a slit, and then, or you can trap 4 particles. You can use a dove prism to rotate them into the plane of the table. That's important when we actually build a cavity around. You change the frequency of the radio frequency tones, and you can change the distance between them, and you can use the scattering of the light, so the interference, to calibrate the distance. So you use the lambda as an etalon in your setup. Then, of course, this is how you trap, and then the light coming back from these particles. So the light goes in the right direction, and then it's reflected, some of it left, and this light has information about the particle motion along the optical tweezer. So we use a Faraday isolator to have then split detection. So light from particle 1 goes here, light from particle 2 goes in the other direction. And then we can really recreate how the normal modes of the system split between the two particles. So we can see, at point 0 here, where it's the same optical mechanical frequencies, you would have exactly 50-50 separation of modes. And you can probe, you can have all sorts of interaction types. You can have reciprocal interaction, as I just showed you. You can have unidirectional interactions, so where particle 2 drives particle 1, but nothing in the opposite direction. And you can see that this is the power spectral density of particle 2, and you see only one line. But particle 1, you see its main line, and you also see the line of particle 2 in the back, right? And this tells you that there is coupling from 2 to 1, but there is no coupling from 1 to 2, because you do not see a signature of particle 1 motion in particle 2. Where the lines cross, this is called an exceptional point. At this point, there is only one eigenvector of the system, so both particles move in the same way. That is highly unstable. That's why it flashes so much actually in light. So the particle motions try to explode actually to run away from the trap. If you go all the way to anti-reciprocal interactions, then you split the exceptional point into 2. And in the middle, you have the degeneracy of the frequencies, but you have non-degenerate damping rates of the system. And I will show you in detail how do we actually measure that. So this is in the middle of that region. This is the power spectral density of the motion of both particles, 1 and 2. And the power spectral densities look completely the same. And we tried also fitting just Lorentzian functions, and they look amazingly well fitted. But you know from the math that there should be normal modes of the system that are now a complex combination of Z1 and Z2. And this is not really something intuitive, but because there is dissipation, there has to be an imaginary component in the system. And if you recalculate just based on this measurement, we just calculate these modes, you get one mode that is amplified with a smaller damping rate, and you get one mode that is suppressed with a larger damping rate. And to our knowledge, this is the first direct proof in the non-reciprocal community that you really get such modes. So no other experiment out there can actually measure independently the optomechanical systems like we can. So then we started increasing the coupling rate. So if you don't have any coupling rate in the system or small one, the particle motions, they are completely uncorrelated. You probe that by calculating the relative phase between the oscillations, right? And if there is if they follow each other in phase, that would mean that there would be a peak in the histogram of the phase. Well, this is pretty much flat. And if we increase the interaction, then I don't know how much you see by the naked eye, but you definitely see in the histogram of the phase that there is some certain locking, phase locking of the two oscillators. So they move at the same frequency and they lock to each other. And also in the phase space of positions, you see that it kind of has a small ellipse, which means that there is correlation between the motions. And if you then boost even more, we suddenly discovered that the state of the particle motion completely changes. So this was all Gaussian, right? So these are, if you cut through, you can fit a Gaussian function, but now here you get something that splits. You get kind of a bimodal distribution in the phase space, and it's locked even better than before. And you see that the amplitude of the motion completely blows up to like half a lambda in amplitude. So there is. It's known that as soon as you generate these anti-reciprocal interactions, I can go back just to show you, the eigenfrequencies, right? They have imaginary component, which is a damping rate. And if you look into this one, it's a damping rate minus the coupling rate. And if the coupling rate grows larger than this, then you have negative damping. And this is the amplified mode here. So it actually starts narrowing more and more and wants to blow up. And what happens is that now the nonlinearity of the interaction that we have comes into play. So it turns out that the nonlinearity itself, you can do an analytical calculation, results in a limit cycle behavior of the motion, which is basically mechanical lasing. So if you want to fit the state of this oscillator, you get actually a coherent state. So you go from something that is a thermal state of motion to something that is a coherent state of motion. And this is the theory of everything, right? So this region between the dashed lines is where the eigenfrequencies will be degenerate. This is what I showed you in the previous slides. Number one region, which is this white region, says that it's linear motion, and above this full line, solid line, which is called Hopf bifurcation, you get actually nonlinear motion or the limit cycle behavior, and the color just shows you the size of this of the amplitude of the limit cycles. So we did the same experiment, and we could exactly see the predicted analytical behavior in the system. What I won't show you, but we also see, of course, as the system crosses all of these lines, first into the dashed and then also into the solid line, on both of them, we see diverging fluctuations. So they're signatures of phase transitions. We even know how to define a phase transition or thermodynamic limit. That would mean that the number of phonons goes to infinity, but this is a classical system, so we do not detect single phonons. And then it's hard really to argue that it's a phase transition, but we do see all of the signatures of phase transitions. And last, just a couple of minutes. So also in parallel to these activities, we've been working on yet another experiment where we integrate these optical tweezer arrays in a high finesse cavity. And the problem is, because these particles are big, if one of them gets lost and falls onto the cavity mirror, you lose the finesse. And it's almost impossible to clean it because it's really small. So the best that we could do is to recover is to use this polymer it's a liquid that you put in the cavity mirror, it solidifies, and then you pull it off. So we had to develop novel methods of loading particles in high vacuum, and we use a hollow core fiber. So it's a fiber that has air as a core. And you can actually see here in the experiment how everything fits together. So what you see here in the front is the tweezer lens. That's where the tweezer arrays of lasers come through. And then you see here a hollow core fiber. So maybe I show it with my finger. This is a ferrule that holds the hollow core fiber. And here, the extension of the ferrule, you see the hollow core fiber hanging. And you have two cavity mirrors forming a high finesse cavity that is near concentric. So it's actually close to the instability regime of the cavity itself. And now we are able to really bring the particles through these hollow core fibers. So this is our scientific chamber. This would be the loading chamber, where we actually have a spray of particles. And then we have a standing wave inside of the hollow core fiber, which you can move by detuning one of the laser beams, and you can pull one by one particle and populate the optical tweezers. You can spool this optical fiber, hollow core fiber, on this Thorlabs mounts. You have a small footprint on your table, and here is how the particles are moving. So these are two particles following each other, and then the third one, which is probably a cluster, will come along. And this is 2-meter long spool, so they go around like 20 times until they actually then come out to the other side. And at the other side, you go through a flange into the vacuum chamber. Funnily, this method of actually putting the fiber through a flange into the vacuum chamber was invented by Eric Cornell back in the time. And now we can populate tweezer arrays inside of an optical cavity. So we can have a 1D array or a small 2x2 or 3x3. And then we could go up to 5x5, but we also wanted to progress on other aspects of the setup. So what we did is we just changed the distance between them and wanted to see what's gonna happen. And the middle one just escapes immediately, probably already because of some stress and in the geometry of the system. And then some other ones disappear later on when you're really close. So these are the studies that we can do and that we want to do later in the future. And we already have them in the cavity, and the cavity cooling is working now, but I don't have nice data to show you for that. And in our new lab, what we are also starting is hybrid systems, because interactions do not care what's actually trapped, as I told you. So you can trap two particles, you can trap two atoms, something that I did in collaboration with Vladan Vuletic from MIT. And you can then cool them atoms into the ground state. So this is going to soon go on archive. Or you can trap a single atom and a single particle, and then you can let them talk, and you can harness the quantumness of the atom for the levitated nanoparticle. Or looking at it the other way, you can use the atom as the probe of some of the questions about nanoparticles that we don't know. So for example, as soon as you have all of this in a cloud of atoms, for example, we want to do cesium, there's going to be a layer of cesium atoms also on the particle. And general people thought that it's a monolayer of cesium, but that modifies already Casimir interactions significantly. So actually using the atom and looking into the shifts on the atomic transitions, you can probe how does the particle react with cesium atom cloud. On the other side, also, as I said, blackbody radiation of such nanoscale particles is completely unknown. So it definitely does not follow Stefan Boltzmann law, but it's unknown what law does it actually follow. And again, I mean, you can observe the blackbody then forces on the atoms. So similar experiments have been done. So blackbody radiations on atoms have already been observed by Holger Muller at Berkeley. So, and again, other nano objects, so nanopillars, anything that is smaller than the wave. So to just summarize, so this is my team. This is a picture from 2 years ago. We now need to take a new picture because we have quite few members added. And yeah, so with Vladan, we've done a lot of things on atoms and cavity cooling, and Ben and Kanu have been our theory support on many things. And yeah, so with Marcus, I've collaborated for the previous 15 years, and we will continue to collaborate on such topics. And with that, yeah, that's it. Thank you for your attention, and looking forward to discussions.
Thank you for an excellent talk. So for this session.
You're using some visible light to do the trapping. Why this wavelength? Many wavelengths smaller than the particle, so why visible?
Yeah, so glass absorbs a lot, right? So we have to use infrared actually. So we use 1064 or 1550. So in our previous experiments, we've done 1064, and we could estimate from the measurements that the particle temperature goes up to 700 kelvins. So imagine you have a particle where its internal temperature is 700 Kelvin, and you manage to cool it to the ground state of motion, which is 10 microkelvin. Right, so this is what we've done in the past. And now in 1550 laser beams, we know that the temperature is much smaller than that. So it's closer to the environment temperature. There is no better wavelength. And then again, the question is, as soon as we have a hybrid system, we of course will have to trap also at the cesium wavelength. That's why cesium, because it's kind of the furthest away into the infrared. So let's see then what the temperature of the particle will be. But also all of the components that we use, of course, readily available at 1064 and 1550.
Very nice talk. There, lots of interesting topics there. I was wondering with the black body radiation we were discussing. So it sounds like the particles they heat up. You're reaching maybe 700 Kelvin or something like that. How do you determine the temperature, and what are kind of the challenges in determining the black body spectrum if you want to compare to Planck's law?
Yeah, this is so there's many aspects, many answers to this question. Okay, so how do we determine the temperature? This we know from a model of gas damping, actually. So you know that silica, actually, the gas molecules do not just elastically bounce off. There is accommodation of gas molecules on the surface. And this means that the gas molecule comes at 300 Kelvin, but because it actually sticks for a while, it comes out with a significantly larger temperature. So if you measure gas damping, you see actually discrepancies to the simple model where it's an elastic collision. And you can deduce accommodation coefficient of something like 60 to 70%. So that's how many gas molecules stick. But you can also estimate then the temperature, the surface temperature of the body itself. And that's why I know that it's 700 Kelvin, but this is like 700 plus minus 150 or something like that. So you cannot really measure it that well. But that's the atom, right? I mean, with the atom, you can measure really precise shifts. And the model of radiation, or I know that there have been experiments with microparticles. So if you start with a microparticle of something like 100 micron, then it's a big body. So the thermal wavelength is something like 10 microns or something like that, if I remember correctly, 5 to 10 microns, depending on the temperature. And then what they did is they used a CO2 laser to melt the particle while being trapped. So the particle would actually shrink in radius, and they started seeing in the tail of the black body emission spectrum, they started seeing me resonances, right? So this is the first effect that you would observe when you go down in size. And then you pass this on and you go below the thermal wavelength, and then you have to look into the bulk. So typically the Stefan Boltzmann law assumes that you have kind of steady emission at all wavelengths. Well, silica actually has an emission peak at 10 microns. This is also the absorption peak, and that's why you can use the CO2 laser to melt it. And if you just take the spectrum of bulk silica, you can fit a couple of these resonances in this range, and then you can calculate, the emission goes with the surface, and you get to something like temperature square in the emitted power. So Oriol Romero Isart, now the professor at ICFO in Barcelona, he has done a couple of works on this theoretical modeling. So that's something that we hope to observe in the experiment, actually, to see we can heat it up easily. So we would see then again, how does it scale with the temperature?
In the experiment, you go to 2 dimensions with the particles. How do you experimentally trap them? Are you using SLMs or multiple beams?
Yeah, so we use now we use acousto-optical deflectors exclusively, so 2-dimensional acousto-optical deflectors, and then geometrically, of course, the problem was. If I go there, this is already zoomed in. Yeah, so if I go there, you can see, right? I mean, the tweezer arrays will be like that. So you would have like a 2D structure like this, and the hollow core fiber comes from top, right? So you have to start from the bottom traps, and then you generate the next level of traps, and then you fill it up, and then you generate the next level. So it has to be done in these steps, slowly being populated within. So this was a little bit of a difficulty. Yeah, and I have to say, if you're interested in the technology, I'm happy to share one of the most amazing things that worked out of the box. As I said, it has to be a standing wave inside of the hollow core fiber. So we actually, in the bottom here, we have a lens that has laser beam focused into the hollow core fiber, like here. And as we move the hollow core fiber, we install the nanomax stage from Thorlabs on the outside of the vacuum chamber that tilts the laser beam. So it automatically locks the coupling of the laser beam into the fiber. So you use AtoCube to move the hollow core fiber, and the light is constantly coupled into it, which is, I couldn't believe that it works out of the box. So yeah, that's why we can now trap these big, large tweezer arrays.
Is the motivation for the higher finesse cavity? Is it just for cooling, or?
Yeah, so original idea, actually. So when we started this experiment, our previous experiment with the cavity was on ultra strong coupling. So where the coupling rate was larger than the mechanical frequency in the system. And in our particular system, this would lead to some unstable behavior, and this could lead actually to really strong squeezing. And this is, of course, now pushing this in the field. When you cool the particles to the ground state, it cools down to 10 picometers. That's the size of the wave function. So the only way to apply some nonlinear optical potential to it is first to squeeze the motion. So you squeeze the momentum, you anti-squeeze the position, and then it sees the optical potential. But you have to do that by 30 dB or something like that. So huge. And ultra-strong coupling, in principle, in theory, could do something like that. So we did some first study of that. And then we built yet better cavity to have even larger coupling rates. And in the meantime, well, we saw that there could be also interesting studies with tweezer arrays. So we actually now have a setup that can do both. Yeah, it's actually, the cavity is too good to do cavity cooling. So you have to actually, in order to do cavity ground state cooling, you need to displace the particle from the cavity axis by 40 microns, and the waste is 20. So you have to be quite far away from the cavity in order to do ground state cooling that you do not have ultra strong coupling.
So I find it quite amazing that you can get into the strong coupling regime just from having them near each other, and scattering, like unstructured scattering in 4 pi is enough to strongly couple them. How far can you push that? Like, can you get into ultra strong coupling if you bring them nearer, or will they, bump each other out?
Yeah, so in order to, there's always this, we ask the same question. So in order to entangle them via any interaction, you need to be not in the limit of strong coupling. I mean, our strong coupling is stronger than the damping rate in the system, but it has to be stronger than the decoherence rate in the system. And this for us is impossible to do. So that's why we need a cavity. We need a cavity to enhance that. Or one could do near field optical interactions, so to bring them close. The closest that we could do these days, if we cool them in the motion, so if they're at 300 Kelvin, it's 2.5 microns, but if we cool them, we could go down to 1.5 micron, which is 1.5 times the wavelength, right? You can imagine that a double well that you create a double well, which has a really small barrier, right? So we do want to probe near field optical interactions as well. And because we cannot do it with particles, that's why we now have collaboration with the group that creates nanopillar arrays, and they can be, of course, at any distance that you want. And we hope now in June to get some of these samples to actually probe these interactions between them. So these are super soft. They oscillate at 1.5 megahertz, and yeah, they're, I don't know, I can tell you more about it if you want, but.
Talk more about it during the lab tour, because there's some tabular arrays that Alice and Dave have been measuring.
Cool.
Great. Well, let's thank Uroš for the talk.